How finely crafted this ship of fools, sail and beam, fleeting flesh and bone. Who? All right. So what I'm showing you here is the Edwin Smith papyrus. And it could arguably be said that this is the first, or at least the oldest existing medical text. It's about 3,600 years old. And so that's 3,600, almost 4,000 years ago. This was a medical text. And specifically on how to deal with surgical trauma. You are a person that was in a battle and got your arm hacked up. How do you keep that soldier from dying? Or you were dealing with an accident and got in the head. How do you keep the person alive? I don't know, that kind of thing. As a text on surgical trauma. The reason I'm showing you this is to underline the idea that what we're doing in this class right now is a little bit different than what you may be doing in any other class. This is super. But the point is that studying how the body works and how to deal with what goes wrong with it, physiology and human disease, is incredibly old. And so there have been literally thousands of years of people sitting in those chairs. And you are part of this tapestry of humanity that goes back generations, back to the horizon. So I want you to understand that and have a sense of it as we talk about this, that you're learning something, we're learning about the human body, but it is a part of a very old tradition, There's something special about it. And what's particularly interesting about it is that the thing that we're studying, the human body, hasn't really changed at all since this time. All right? The technologies of so many other fields, the technology of theater. Theater changes, understanding of theater changes depending upon the aesthetic, the approach. The human body is the same as it was. It's just our understanding changes and our ability to deal with it changes. But the physiology, the underlying physiology is the same. All right, so got to give some props to this dude, Hippocrates. Hippocrates was a Greek physician. I'm going to go through a bunch of the history to really give you a sense of that lineage that considered to be the father of medicine. I guess the mother of medicine would have been the countless women that tended to the sick and ill throughout the eons, but are not. He lived in the 4th century BC, and he did a lot. He was a uroscopist. So that means that he would try to diagnose disease by getting you to pee in a glass jar, and he would look at the color of it, and how frothy was it, bubbles. He'd smell it, he'd take a drink of it, see what it tasted like, and then diagnose your disease. That was one of the things. Seems like he might have been a little out of his mind, but he wasn't actually. He established, importantly, the Hippocratic Oath. Has anyone heard of the Hippocratic Oath before? Yeah. More than that, yes, but yes, correct. Yeah. Yeah, certainly that. Yeah. Solemn oath. It's a solemn oath to seek the cause of disease and to always act in the best interest of the health. Always act uh, to the benefit of the patient. He had an important contribution, and this was at the time uh, pervasive in Greek culture was the idea if you were sick, it's because you pissed off a god. You pissed off a god. You did something that made this god angry at you, and they afflicted your. He said, no, no. There are natural causes. There are natural causes. Yeah. Seafood. Um, a lot of the proscriptions in dietary prescriptions in the Bible are there because they have real health consequences. So the thing about, for example, not eating pork as being not kosher or seafood, this is because in pork it was common to get trichinosis at the time. They didn't know what trichinosis was. They didn't understand it. They said, "Don't eat pork; it'll mess you up." And seafood, it's easy to get salmonella from seafood. So they said, don't eat seafood because and they yes, God they rationalize it in terms of the deity, but there were actual sort of health reasons, kosher or halal. Yeah, right, right. Yeah, and I think Hippocrates was trying to get past these. Certainly, the code in the Torah about what to eat and how to eat it is older than Hippocrates. Uh, those are writings that were actually around the same time as papyrus. Um, and this Hippocratic oath became codified and got passed down. So right here is a copy of the Hippocratic Oath written in the Byzantine Empire in the 12th century, Turkey, what is today Turkey. So it was propagated. Next person, the sort of next generation after Hippocrates is another Greek named Aristotle. He was born in Chalcis, and he took this idea of Hippocrates, and he said, okay, all right, there's a lot of controversy, right? People were like, whoa, Hippocrates, slow it down, dude. You're going to anger some gods. You're a little crazy sitting there drinking everybody's urine. Let's come to terms with this. I don't want to throw everything away. Let's say that you still can piss off gods, and that can cause disease, but it's a supernatural cause. We're going to call the study of that theology. This is where we get the word theology. And then he distinguished theology from physiology or physiology. And that was these natural causes. So much like Shakespeare invented a lot of language in English, Aristotle invented language for the Greeks, and he made this distinction of theologi and physiologi. Aristotle was amazing, right? You can dedicate your entire career to the study of just aspects of his as an academic. One of them was that he believed that complex structures are built from simpler parts, ad infinitum. All right, so that there is no smallest thing, that things can be infinitely subdivided. Yeah, this is a kind of a thought experiment, right? I have something, I'm going to cut the cookie in half. Well, I'm going to take that half a cookie and break it in half again, etc. What's to stop me from keep dividing the cookie in half forever, right? It turns out that this doesn't square especially well with our contemporary concept of physics right now. Atoms, whatever. So this turned out in the broad arc of time to not be the concept that he embraced. He also incorrectly believed that nerves were controlled and originated in the heart. And he was really confusing ligaments and nerves. And he thought, but they had an understanding of nerves, and if a nerve got cut, a muscle didn't, or something like the life of the limb, dark. But he thought it came from the heart. He believed that the heart was the center of the and all of the action emanated from it. Even though both of those things turned out to not be completely true, we still give him props and love Aristotle. All right, on to this guy, Claudius Galen. We're switching from the Greeks to the and Galen is quite a character. We're going to come back to Galen again and again. He was remarkable. He's one of these kind of guys, like, I don't know, maybe in history class, or they probably don't have classes. If you've ever had an ethics, conversation in an ethics, in a class about ethics, there's the question, the research, the horrifying research that the Nazis did during II uncovered real aspects of how the human body responds. Right? There was actual things that were learned, as horrifying as the work was, and so there's like a debate that you could what happened to that? What happens to understanding? Should be used or not? What happened? Find how it was collected, abhorrent. But anyways, Galen got there way earlier, man. This dude was doing some edgy stuff way back in the day. He was the surgeon for the gladiator. And so the Romans, like the Greeks, did not believe in cutting up human bodies. They didn't believe in autopsy. They didn't believe in human design, which is really why Aristotle got the heart, nerve, ligament. Because he didn't have the time to do, he didn't have the ability, the cultural ability to go through and do a careful dissection, understand what parts is connected to what parts. Galen, it was the same for the Romans. They did not believe in human dissection. Once you die, stick them in the ground, and it's all over. Well, they weren't really experimental. They weren't especially experimental. Galen certainly was experimental, but most of his experiments were like when we get to the kidney chapter, I'm going to tell you a charming vignette about how he discovered that the kidneys make urine by clamping the ureters, a living monkey. That's the kind of guy Galen was. Anyways, but he was the physician to the gladiators, and so because of that, he didn't have to do the dissections themselves. The gladiators would sort of dissect each other out in the Colosseum, and then he would get the leftovers, and he got a very intimate view of the body. And because of that, he learned a lot. Yeah. So he saw science. He also began to think about science in a more modern context. He saw it as a method of discovery, not just like a body of facts that you take on faith, that you add to your understanding, right? There's perhaps a method of adding to your understanding. Maybe we don't know everything. Maybe Aristotle wasn't infallible. So this guy is like, 400 years after Aristotle. Like 100 years after, or whatever, 150 years. So, yeah, he would say that trust what you see. He was what's called an empiricist. Based on his understanding was based on empirical evidence. E-M-P-I-C-A-L. Empirical, meaning observational. I know that the sun is shining because I can see it. I can go outside. And so he told people to believe your senses, to believe what you are experiencing, more than taking something. This, and I'll get to you in a sec. This right here is the foundation for the ideas of who would become the originator of modern science. Does anyone know who that is? Who would you, if you had to guess, one person who brought us into the modern age of science, the very first person, who might? Before him, and I'll give you a hint, it was a French. Yeah. Oh, very good. Okay, so Darwin was the theory of evolution, right? And Louis Pasteur actually, I believe, came after Darwin, and Louis Pasteur was a Frenchman who understood, he began to explore microbiota, relationship to health. Not Louis Pasteur, he was French. We talked about this person in the trig class when I was talking about, you guys asked me about the Cartesian coordinate. He also invented that. Huh? René Descartes. And he said, cogito ergo sum. That's the foundation of modern science. Cogito ergo sum. Cogito, I think. Ergo, therefore, sum, I am. I think, therefore, I am. And it was this idea that I'm not going to assume anything, right? I'm going to strip everything away, and which is what he's saying. Don't take things on faith. What are your assumptions? I'm assuming that there is some god named Zeus, and he's going to be pissed off at me, or I guess for this guy it would have been Jupiter. And if I don't do what he says, he's going to give me a problem. I don't know, a flu or something. You've been so patient. What you? Sure. Well, no. This would mean like Aristotle and Plato and Socrates, because honestly, he tore Aristotle up, right? He did not. He was not impressed by Aristotle. He would say here, I'm gonna read you a quote. What's up? Don't disconnect, please. Disparaging those who know nothing of what is to be seen in dissection. Right in your face, Aristotle. Come on. I have shown in my book, available on Amazon, on the teaching of Hippocrates and Plato, that the source of the nerves of all sensation and of voluntary motion is the encephalon, which is what he called the brain, and that the source of the arteries and the innate heat is the heart. Come on. It's up here. There we go. Yeah, so he was able to figure out that it's the brain that's running the show, and or at least where the nerves are coming from, and it was the heart that is where what he called the innate heat, because they understood that humans were warm-blooded. All right, they began to understand that humans are warm-blooded. A fish, you can freeze a freaking fish and it'll come back. Not all fish all the time, but that's pretty intense. You cannot really do that outside of it. All right, so we're gonna this is like a real hop, skip, and a jump. We could have a whole course dedicated to the history of medicine. I'm just hop, skipping, and jumping along. Here's a couple others, just so that we don't live in a purely Eurocentric, anglicized reality. If you don't, here's one guy named Avicenna, who I don't know. Maybe it's a bit of cultural prejudice that he lives under the shadow of Galen and is called the Galen of Islam. But he definitely was able to reconcile Galen and Aristotle and take them into account with his contemporary discoveries. He wrote a book called The Canon of Medicine. And his real strength, Avicenna did a number of things. One of them was that he was able to collate all of the anatomical and physiological and medical knowledge of the time into a single book and sew it together, so to speak, with his own observations and explorations. And it was so thorough and well composed that it became the medical textbook all the way up until the Age of Enlightenment. So like 500 years. 500 years, while the rest of Europe was mired in the Dark Ages, right? The medieval period, which was not a period of exploration. It was a time of the dominance of the Christian church and a real, which acted as a wet blanket on inquiry in Europe. It was actually the Islamic world that where that spirit of exploration and free inquiry lived. He also made a very careful study of muscles and understood he began to understand the mechanics of muscles and muscle agonist and antagonist pairs. Another guy, Jewish person named Moses ben Maimon or Maimonides, came a little bit after Avicenna, wrote a slew of very widely used medical texts, and he was the physician to the Sultan Saladin, a very famous sultan in Egypt. So he had enormous wealth and resources at his disposal for his medical research. Okay, sure. I'm not going to quiz you on dates or, truthfully, probably any of it, but maybe. I mean, I think it's good for you to know, to understand the history. History is a good doorway into learning anything, frankly. Medicine, there's a rich history. Then comes this guy Vesalius, all right? And this is about the time that Avicenna's book is falling out of favor. And Vesalius, we're in the Enlightenment here, the Renaissance period is happening, and the church is like coming to terms with this groundswell of interest in science. Enter this guy Andreas Vesalius. He was Flemish. He lived in Flanders. It's not Ned. It was in the Dutch lowlands. And the Catholic Church let up a little bit on the concept of cadaverous dissection and autopsy. This was for a number of reasons. One of them being that Europe had just been decimated by the plague. And sitting down on your knees and praying was not working very well for you. And so this idea of Aristotle, of theologi and physiologi, was reinvigorated in the Catholic Church, and they released their restrictions on the dissection of cadavers. And what was interesting about this guy, he was, again, one of these people truly in the Renaissance tradition, where he was a careful observationist, a careful, we'll say scientist, although maybe not in the absolutely modern sense of the term. But he was also an exquisite artist. And he published this book, De Humani Corporis Fabrica, on the structure of the human body. And it is stunning. It's stunning. It's a series of hundreds of plates. I have the book. I could not be, but I have a copy of this book that I can bring in sometime if you want to see it. There are these amazing dissections of the human body. And for the first time, people were able to see what they were made of. This profoundly human pursuit, right? This frontier that every person is walking around with in the form of their own body. This frontier for exploration was beginning to be revealed. And so he had this school set up there, and people would come from all around and watch him do these remarkable dissections, and then he would make these stunning plates based upon his dissections. And his book, published in 1843, was used for a very long time after that as well. All right, there's a bunch of other guys. I don't know. These are important. I don't want to call them bit players, but they're maybe not the heavyweights that Galen or Vesalius were. Just a few bits about them. This guy, Servantis. I'm skipping along over them, but there's interesting stories to these people's lives, nonetheless. So Servantis, he is the one that kind of took the observation of Galen about the innate heat of the heart and whatnot, and realized that it's blood that has to circulate through the body. All the organs need blood, and it's the job of the heart to send it out, and then it returns. All right. This guy, William Harvey, was a British, and he was one of the earliest experimental physiologists. So Aaron was asking about the kinds of experiments that Galen might do, and I said they weren't really experimental; they were observational. Harvey was the first guy to do actual physiological experiments in any great number. And he was working in the same sort of vein as Michael Servantis in terms of circulating blood, if you'll excuse the pun. All right, this guy, Robert Hooke. It's important to talk about Robert Hooke because Robert Hooke expanded the palette of our investigation of the body. Up until this point, everything that we have talked about, and I don't have somebody else. Okay, good. Up until this point, everything has been macroscopic on the scale that you can see and touch with your own eyes. But Robert Hooke was inspired by people like Copernicus and Galileo, who had these telescopes using multiple lenses to look very far away. To him, he said, I want to use these lenses and use more than one lens and look at something very close. So he made the first compound microscope that was really functional. Right? The first really functional compound microscope that had compound, meaning it had two lenses. There was the oculus, which was the small one that goes by your eye, and then the objective, the big one that was the object. The oculus being ocular for your eye, and the objective the object. He also had this set, so this would be his first microscope, and he had this set of lenses that would take sunlight, and concentrate it down onto the thing that he was looking at to illuminate it more brightly as well, so he could get a really good look at it. And because of this, he was the first person to really see and name cells. He's the first person to identify cells. And does anyone want to guess why he called it a cell? What else do you know that word? Yeah, a jail cell, a room, what were you going to say? A plant cell. Well, yeah, plant cells are, that is the meaning that he applied. But these two they put their finger on where it came from. And very close to a jail cell, it was actually the cells, which is what they were called, that monks in the church would go into. And you'd live in a monastery, and they would live literally in a closet-shaped box, right? Just a little box with their straw mat and whatever they had in there, which is probably nothing but a wooden cross or something. That was their cell where they would go and mortify them, whatever. And he looked at Hooke looked at a cross section of cork. He had some cork. I don't know, maybe he was drinking. Who knows where he got the cork? But he took a slice of cork and he stuck it under his microscope. He's like, cork is weird. It's wood, but it's not any other kind of wood. I want to look at it. Sliced it up, and this is the drawing that he made of it. And he saw these little squares, and to him, they looked like the cell in which a monk. And he began to call them cells. And so he made this amazing book of microscopy, these amazing drawings. And he called it Micrographia, small, really small. And that came out in 1665. Oops. The what? Oh, there is it. Yep, that's from summer camp. Okay, come on back. What happened? Here we go. All right, I'm skipping way ahead again. And the last person I'm going to land on is this guy named Louis Sullivan. Now, Louis Sullivan was an architect. He was an architect. He's most notably known for being the inventor of the skyscraper. All right? He was the first person to build a skyscraper. It's actually, this is it. Has anyone been to St. Louis before? Well, if you've ever, did you go to see the arch? Yeah. If you were standing and the arch was right there and you were a little, and the river's behind it, and you were a little bit off to the left, looking at it, kind of far away, but still no buildings obstructing, and you were to turn around 180, that's what it's that building. That was, and he did that by building. The idea was to build like a steel frame underneath as the skeleton of the building, enabling it to go up higher, and then instead of just stacking the steel frame under a building, enabled this building to be built up. And he had his own aesthetic thing, blah, 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 blah. But he wrote this book called The Tall Office Building Artistically Considered, right at the turn of the century. Why the hell am I talking about him? I skipped Darwin. I fully skipped Darwin, didn't I? I skipped Louis Pasteur. These are important people. I didn't even talk about Descartes, except as a footnote to Galen. I'm talking about it because this guy loved Darwin. He thought of himself like anyone who thought of themselves as educated people in the day. What's up? Being a person who would be familiar with Darwin, trying to understand it, what was being said by Charles Darwin. And here's a quote from his book. It is the pervading law of all things organic and inorganic. So when he's saying inorganic, he's talking about building. But when he's talking about organic things, he's not talking about building. He's talking about things that are alive. So he's saying he's looking for a first principle here. He's looking for a first principle. It is the pervading law of all things organic and inorganic, of all things physical and even beyond, into the metaphysical realm, like our ability to come to terms with things that do not fit into modern science, right? So he's trying to really come up with this grand statement of all things human and all things superhuman. He's looking for a first principle of all true manifestations of the head, the heart, and the soul. Okay, what is it? You got us holding our breath here. That the life is recognizable in its expression. What does that mean? The form ever follows function. This is the law. So, what is he saying? He's saying that the structure something has is dependent upon the function that it has to serve. That seems like something super, right? Like a wheel is round because it needs to roll. But actually, this is the first time that what we call the structure-function paradigm was ever articulated. First time anybody ever stated this relationship between the structure of something and its function. And we're going to come to terms with what that means and why it's important in a minute. That minute has arrived. Enter two concepts here: anatomy and physiology. Anatomy is the structure of the body. What are the parts? Where are they located? How do they relate to one another? This can include spatial relationships, that my exterior obliques are perpendicular to the interior, superficial to them. Both gross anatomy, and I'm not talking, when I say gross, I don't mean, put that anatomy away. I'm talking about large anatomy that I can see with my eyes, or microscopic anatomy that I need one of Robert Hooke's compound microscopes. French. Gros. That's right. Gros. Yep, as in large. Good. So this is the structure, and then physiology. The word recurs. Aristotle's word recurs. It is the function. It's the function of these anatomical structures. So there are individual functions of the parts in the body, and there are cooperative. So one little part is going to have its individual function. Do I need to, by the way? But it's going to work in concert with other parts. This involves a lot of things. Physiology draws on a lot of different chemistry. There's a lot of chemistry. I'm going to assume that you have a basic concept of chemistry, but I'll remind you. Biochemistry. That's the chemistry of biological. Genetics. How the genes, the DNA in your body. And then fundamental biology. All of these are components of physiology. All right. So this hierarchy of complexity. Aristotle, I told you Aristotle thought that things were made up of simpler, and so on and so on. And so this is kind of a reflection of that, except there is a starting point. Atom. There are these different levels, organizational levels, when we're going to think about how the human body works. There are atoms, which make up molecules like water, glucose. Those molecules, some of them can form macromolecules. So, for example, the purine or pyrimidines, A, T, G, or C, can polymerize and form chains of macromolecules. DNA or proteins are macromolecules. Complex polysaccharides, these are macromolecules. Macromolecules, then, a number of them come and form together these organelles, which are the small components of a cell that hopefully you remember talking about. And then there are cells. Cells come together either, usually with multiple types of cell, to form a tissue. There's all kinds of tissues. Multiple types of tissues often come together to form what are called organs. Organs are macroscopically functioning structures that are distinct from their environments. And they are part of an organ system. So, for example, here is a stomach, and it's part of the digestive system. And so an organ system is a group of organs and related structures that are working in concert for one or more specific purposes. And then an organism, little baby, made up of multiple organ systems working together. All right, so that's the hierarchy of complexity, the levels of organisms. We can think about this along a size scale. So here is a person, and they're a little over a meter. The average person's about 6 feet tall or whatever. And here are these different size scales. This is a logarithmic scale. So each hash mark is an order of 10, an order of magnitude smaller than the one below it. And an atom is about a tenth of a nanometer in diameter. All right? An angstrom. A tenth of a nanometer. And So these are where all of these different structures fall on that size scale. The one thing I want to point out is the human oocyte right here. This is an egg. So women are born with the full complement of human eggs that they need in their life. In fact, there's more than 150,000 of them in each ovary. But those human eggs are about a little larger than 100 micrometers. That is the smallest thing that is visible with the human eye. So that's kind of a beautiful poetic thing, that the smallest thing that you can see is precisely the size of the human egg. So, which is right here, right? So this is what we can see with the human eye. This should be scooted a little bit. Sharp eyes can catch. And then we have these compound light microscopes of Robert Hooke's. And then we get down to these other methods, like a scanning electronic microscope, a transition electron microscope. There's a new form of cryoelectric microscopy that can go even lower and visual atoms. Yeah. Cryo just means it's that like super. Yeah, the Nobel Prize in chemistry developed it last year. All right, so here's just another look at these levels of organization, going up from atoms and chemicals to macromolecules and cells and tissue and organ into the organ system. But I like this slide because it shows you all of the organ systems that we're going to talk about. In that book that I gave you, it's chapters 5 through 29. Chances are very high that we're not going to get to talk about all of them. We will touch on the integument, meaning the skin. We will definitely talk about the skeletal system, the muscular system, and the nervous system. Those are all big. Probably won't get to the endocrine, but that's the chemical control system in your body. We will talk about the cardiovascular system. We will not talk about the lymphatic system, probably, which is your lymph drainage. The respiratory system, we will. Digestive, we will. Urinary, we will. And we will not. So that's what I hope to talk about. If we have time, we'll talk about more, but I doubt it. Even that is pretty ambitious. All right. So why did I put this picture up here? This must have been, I haven't revised these slides since last year. This was the picture of, these are pictures of a scanning electron micrograph. So these are diatoms, like little teeny tiny creatures. Ocean. They look like, I guess it's a prettier picture on my computer than it is on the screen. This crazy thing right there, that beautiful picture, is a macrophage. That's an immune system, and these are bacteria here, these little balls. This crazy blob looks like it's blowing out. These are pseudopodia that it's using to find bacteria and surround them. These are the kind of images that you can get with scanning electron microscopy. All right,